Hello and welcome to my talk on our paper, The Effect of the JPEG Implementation on the Cover Source Mismatch Error in Image Steganalysis. This paper is joint work with Nora Hofer and Böhme. My name is Beneš and I am a PhD student at the University of Innsbruck in Austria. This presentation is structured as follows. First I recall how JPEG compression is implemented and then I explain the cover source mismatch phenomenon in Steganalysis. From there we move towards the empirical part. I explain the experiments we ran, the results we obtained and discuss them briefly. Ready? Let's recall what JPEG is. JPEG is a popular standard for lossy image compression. The de facto standard implementation for JPEG compression and decompression is libjpeg, an open source C library. Since 1998, 13 new versions of libjpeg were released. Popular forks of libjpeg are libjpeg Turbo, which uses accelerated SIMD instructions, and mosjpeg, that is optimized for the web. In our previous paper, we studied the differences between different versions of libjpeg. When analyzing 13 versions of libjpeg and one version of libjpeg Turbo, we observed 3 different outputs for compression and 3 different outputs for decompression. And this is without changing any compression and decompression parameters. The figure shows the sets of versions producing identical outputs and where the differences occurred. You can see that, for example, for compression in orange, version 6b and Turbo produce exactly the same output, but it is different from the output of versions 7 and above. Also note that the pattern differs for compression in orange and decompression in gray. If you're interested in the causes of this, check out our previous paper. Here we deal with the effects. The previous paper also shows that the greatest difference in output was between version 6b and 7. While visually imperceptible, these differences could be critical for certain applications in multimedia security. One such application is Steganalysis, based on machine learning. Its aim is to detect steganography, that is, secret messages hidden in inconspicuous cover media. However, the model's performance has been observed to degrade when a cover source of training data differs from the cover source of test data. In the literature, this is called cover source mismatch, or CSM in short. We start with a scenario when training and test data come from the same cover source. In this case, we just measure how hard it is to detect the existence of a steganographic message in source A. We call this the source intrinsic difficulty. CSM is evaluated by training on a source A and measuring the performance on a mismatching source B. For example, source A could be messages taken with a digital camera, and source B could be images acquired with a scanner. This is called source inconsistency. CSM has been a challenge for Steganalysis for more than 15 years. It not only occurs for completely different image acquisition modes, but also when images are processed in different pipelines. Existing research suggests that later stages in an image processing pipeline have bigger impact on the CSM than earlier ones. JPEG compression is often the last step in the image processing pipeline. Therefore, the research question we tackle in this work is, can we find evidence of CSM caused by the differences in the libjpeg versions used for JPEG steganography? Now let's move on how we measure this experimentally. We stick to the well-known scenario and its naming convention. Alice embeds a secret message to a cover and sends it to Bob. Eve intercepts the image and tries to detect whether it contains a steganographic message or not without knowing the steganographic key shared between Alice and Bob. For the experiments, we use 10,000 never-compressed images, randomly chosen from the Alaska database. For simplicity, we only use 2 libjpeg versions, 6b and 7. Recall that these are the ones where the previous study showed that their outputs differ the most. Alice simulates the embedding function JUniword at embedding rate 0.4 bits per non-zero AC-DCT coefficient. Eve tries to detect this with an ensemble of FLT classifiers trained on the JSRM feature set. You can find the references for these methods here in the bottom. Let me explain this choice using the system models from the paper, starting with Alice. JUniword is the state of art. It can be generalized to color images, which is where the libjpeg produces differences between versions. JUniword embeds in JPEG images, hence Alice must use compression. Moreover, JUniword performs content adaptive embedding. This means it decompresses in order to estimate the embedding cost. Now turning to Eve. Her model is a bit more involved, but we don't need to look at the details of the wiring and just look at the level of blocks. The 35,000 JSRM features span two domains. This means Eve's feature extraction involves decompression. Moreover, JSRM uses calibration, a technique involving recompression. This means Eve also needs compression. Note that we set the version of libjpeg jointly for compression and decompression at each stage. This leaves us with two players, Alice and Eve, two selected versions of libjpeg, 6b and 7, and two phases, training and evaluation, altogether 16 combinations. Overall, we think this choice makes sense as we get a good coverage of libjpeg both for Alice and Eve. Now turning to the results. Here you can see the results on the test data from all 16 version combinations grouped into 4 classifiers. The training column describes which versions were used to produce cover stego pairs to train the classifier. You can see that we obtain 1 classifier per combination of libjpeg versions. The evaluation columns describe which libjpeg versions were used to produce test data. The rightmost column contains the total error of the respective classifier on the test data. Let's take a look at the first row. Cover stego pairs for training are generated using version 6b. The same version is used to extract features for training. In the actual experiment, we generate cover stego pairs with 6b, column Alice in the evaluation, and also use 6b to extract features used for classification. In this case, the cover sources of training and test data match. There is no CSM. The error of 29% describes the source intrinsic difficulty. For convenience, we print all intrinsic difficulties in bold. This row describes the source intrinsic difficulty of the second classifier, where all steps are performed with version 7. The error in this row is 30% and thus barely different from above. Here is the situation when the libjpeg version for feature extraction from training data differs from the one used for test data. As you can see, the error increased by 20 percentage points to 50%, which is not better than random guessing. We interpret this as the effect of CSM. Here we change the libjpeg version used by Alice for the evaluation only. In our experimental setup, we do not see much of an impact. As you can see, the error increases only if Eve changes from libjpeg version 7 to 6b. Conversely, when changing from 6b to 7, the difference in error is barely noticeable. Here I showed it on the first 2 classifiers, but the same findings apply to all 4. If you want to know more about our results, check out the paper. From what we observed, we conclude that mismatching libjpeg versions can, in principle, cause CSM in JPEG Steganalysis. In other words, Steganalysis performance may degrade if the Steganalyst, Eve, does not exactly use the same version of libjpeg for training and testing. However, differences in the versions used to produce covers and stego objects, i.e. by the steganographer Alice, seem to barely affect the detection performance. We point out that our results were produced using 1 embedding function, 1 detector and 2 libjpeg versions for which we knew that produce different outputs. More research is needed to find out how this existential result generalizes, how relevant it is in practice, and how to mitigate compression-induced CSM errors. Studying these and various other aspects of CSM in Steganalysis is one of the objectives of the Uncover project, through which this work has received funding from the European Union. Our code and trained models are publicly accessible on GitHub. The code uses Python package I built, which allows its users to select the libjpeg version flexibly. Feel free to check these out. Thank you for listening.